Welcome to Manufacturing Explained. My name is Greg Paulsen, and I have spent my career using various manufacturing technologies to produce and deliver engineered parts. Manufacturing Explained is an expert to expert conversation on all aspects of manufacturing. In this episode, I welcome back injection molding expert Scott Benson, a senior project engineer at Xometry. In my last discussion with Scott, we followed the journey of plastic from raw material to molded part and discussed the various stages of the injection molding process. This begs the question, what about the molded part itself? Injection molding is one of the most design-sensitive processes in the manufacturing industry. You can't just throw any shape at it and expect perfect results. But the fundamentals of injection mold part design are very teachable, and manufacturers like Scott are always happy to help guide a project to success. Scott and I will discuss key benefits of plastic injection molding, such as its ability to create hundreds or even thousands of identical parts daily. We'll discuss what is the minimum quantity you can make with injection molding, and why would someone ask for a mold for only a handful of pieces? We'll also talk about part design tips and what molders look out for when checking part models for design for injection molding, that DFM or design for manufacturing review. This includes my favorite molding trinity: uniformity, undercuts, and draft. Ultimately, it's about discussing how to be mindful in part design to save on those tooling costs. We're going to end with talking about some things that happen along that timeline. For example, can you modify your design after tooling is made? And how and when should you communicate that potential area of design change to your molder? And finally, what is a typical timeline for an injection molded project from design kickoff to first samples, called T1s, to final production parts? Let's jump into the conversation and learn about injection molding part design explained. I am welcoming back Scott Benson, a senior project engineer at Xometry, experienced in injection molding from cradle to grave. On our last episode of Manufacturing Explained, Scott and I discussed the journey of plastic through the injection molding process. This was set from the materials perspective, traveling from a raw material stage, starting as a small plastic BV, and moving through the machine. During this process, the materials melted and fed at high pressure into an injection mold tool. The liquid plastic cools in the tool cavity to its final shape as a plastic part, where it is released and the cycle starts again. So today, let's flip that and start with a part. That thing that designers and product developers are looking to get produced in quantity. I want to learn more from Scott about the benefits of this process and what is crucial to know during the part design stage for the best results. So, welcome back to Manufacturing Explained, Scott.
Yeah, thanks. Glad to be here.
So, I guess for those who missed your last appearance, and I recommend going back to that episode because it's pretty cool. It's a very neat way of going through the molding machine itself. Could you give a brief background about yourself for listeners?
Absolutely. Been injection molding for 13 years. I've worn many different hats within the industry, anything from quality to project engineering to processing. Been around many different types of tools, many different products, many different materials. So there's very few different things that I have not seen. So.
And you said you mentioned something about a master molder certificate. Can you tell me what is a master molder?
Yeah, so there's a company out there that called RJG that teaches scientific molding, decoupled processing. There's a process to optimizing, the injection process, the parameters, and the things that you use. So I have an RJG master molding certificate, and it's an excellent learning tool. They have many different programs, so definitely want to give them a plug here to as a resource for many different companies.
Oh my gosh. So we're going to start with the basics today. Again, like going on that part side and talking about benefits and design. But for us in the industry too, when you talk about scientific molding, that's a whole different thing. It's just such an interesting modern approach to injection molding. But we'll touch on that I think another episode. But it's just really fascinating to learn about.
Absolutely.
But let's go with the basics here. So I'm a designer. I'm making, I'm looking to make something and produce it in some sort of end use means. Uh, why would I choose injection molding? Like, what are the benefits of injection molding?
Yeah, so some of the key benefits are repeatability of the process, the reliability of the process. Basically, you're using an injection molding machine that you can monitor the inputs and during the process, the injection process from pressure of plastic to velocities, get to a consistent viscosity of the material. Um, Basically, you're just looking for that high repeatability for mass production. Not making 5 parts, but making up to millions of parts. You're using the tools that you use to make that part over and over and over again are they're consistent with the injection molding process.
And this would be different from like some other processes. So if I'm comparing it to, machining, for example, like I have a different level of scaling for sure, right?
Yeah, absolutely. So the quick thing is cycle time, right? So machining cycle time for a complex part can be minutes or hours, or it can take a very long time. For injection molding, if I need to scale that up, I can make another cavity and make two of the same part in the same cycle time. And that cycle time can be within minutes. So you can make complex geometries repeat very quickly.
Yeah, and I think that's really big. And one of the reasons why, when I look in front of me, right, everything plastic in front of me is molded right now. Like, I don't typically see, uh, at least in what I would consider like consumer goods, those type of products, anything that would be, traditionally machined or even, other processes like 3D printing and things that you may work at the development stage, moving up to molding, not quite mainstream because molding just has so many advantages when it comes to just making that part with those features consistently and effectively. So you're talking about millions of parts potentially, but are there minimums? Like, could I get a mold of one, or should I get a mold of one, or like what's kind of a normal run for injection molding?
Yeah, you absolutely can get a one part, but you're still going to pay for the machine setup time, the fee of purging out the material and getting the machine set up appropriately. So the single piece price may be very, very high compared to other types of manufacturing. Really, the benefit comes in quantity when you're talking injection molding.
And this is because of the tool, a lot of that, right? So like the tool itself is the biggest upfront cost with injection molding, and what you rely on a lot is the amortization. So we have it. You may be spending sometimes in if it's a low volume prototype or production tool for a smaller part, it may be in like the low to mid thousands, if you will, and then can go up to tens of thousands or even hundreds of $1,000s for a tool. But usually, if I'm spending 100 grand on a tool, I'm probably making a heck of a bunch of parts, and that cash is amortized out really really quickly. And when you make so many parts, all of a sudden, if I make 100,000 parts, it's a dollar added per part, and a million parts, and you're just talking pennies now on the part itself.
That is correct. When you're looking at the return on investment of injection mold, you need to take into account the part complexities that will drive the part cost or the tool cost directly.
Yeah. Now, exceptions, because we were chatting about this right beforehand. We were talking over some of these questions. We talked about minimums. Tell me when you do see like the true minimum. Like, do you ever make like what examples do you typically see when someone just needs like two parts in a molded material?
Yeah, so sometimes you'll run into service products or legacy products where a program has been obsoleted, but they want a replacement part. Unfortunately, during that time, from the time the product was in mainstream to now, that tool may have been damaged or obsoleted or scrapped out. So sometimes we will get one where we need to make a part as molded to a certain shape. Um, Meaning that you can't machine it from a block of material because you may be exposing glass fibers or some polymers, at the surface. They want that as molded surface. as a requirement for the tool or of the part performance. So sometimes you can get into that instance, and those are pretty pricey events, right? Because you're going to make a tool and you're going to make like 5 parts, versus I could just machine that out of a block of material. It would be great, would be easy, but that's just not the way it was designed. So
Yeah, and I know I've seen in my history, also like when I do medical device prototyping, sometimes it's going through, for example, it needs to be go through an FDA approval process, and so even though this is not the production tool, you need production grade results, and I've definitely we've built molds, especially for some like high temp materials that have a essentially end of life after the first run to so whether it's 1 10 15 parts, they just need enough to go through testing and validation, and there's that's part of those expenses sometimes that exist in product development, especially when you have something that's high stakes like a medical device there. So it is just kind of interesting. Once you make that tool, obviously you have some legacy behind it, where that tool can be set up again to create parts. But it's these rare exceptions. Sometimes it just needs to run once, but most of the time, building a tool is more about building that part design relationship where I'm able to get parts at low cost on demand. So talking about parts again, we've switched around this conversation. We were talking materials, going through the injection mold process before, and parts come out. But these parts come from somewhere, right? They're designed. So I really want to spend some time, spend the next several minutes here on just what should a designer be mindful of when developing a part for molding. Like, what are some design tips, and what do you look for when you start spinning the CAD with a customer?
yeah, so some of the easy things, the low-hanging fruit ones are uniform wall thickness. We definitely want to make sure that the shell of your part has a reasonable wall thickness, first of all, from a cooling standpoint, but also is a uniform thickness. If you have an inconsistent thickness, wall thickness, you can find areas of where you'll have read through or sink show up on the show surfaces from ribbing that may be on the underside, uh, mainly kind of in the corners or where those ribs attach, or maybe we have a screw boss. There's different techniques you can use at the base of a screw boss in order to provide structure, but also maintain a thin cross-sectional area. Um, that's probably the number one. Number two would be draft angles. A lot of times as a molder, the greater the draft angle is, the better, because we want that part to release from the A side of the tool. And there also may be some requirements for some pullers to be on the B side, which are basically intentional undercuts that will allow the part to stay on the B side of the tool. Those are very important. The other thing to keep in mind is, parting lines, lines of draw, the way the tool action will work. In a simple two-plate tool, you have one parting line, right? It goes around where the two halves of the tool intersect. You want to make sure that doesn't have a whole lot of features around it. If it can be, if there's a radius you want to put on that edge, just understand that you have to put that into the A side of the tool. Otherwise, it's an undercut. So there's just some things to be mindful of when thinking about how that tool will action around that part.
It's really interesting you talk about this because yeah, when I think about mold design, a lot of times I try to describe people like to our customers about imagine if you had two flashlights, like kind of facing each other, and you took the profile of your part and put it in the middle. And so I'd see like if say one flashlight's one color, one's another color. What the part of that design that's shaded by one color and where it meets with the other color is going to be that parting line, or at least a theoretical parting line of that. And also, I always talk about this: where there's shadows, there's undercuts. So, tell me, like, I definitely see parts. In fact, in front of me right now, I see parts with undercuts. So, like, the side of my laptop has ports for the USBs, and if I shine a light down, they drop a shadow right there. So I couldn't just make that feature with one side of the tool. How are those handled, or how do you approach that as someone who's a tooling expert and talking to the customer?
Yeah, so from a production environment, you want those to be automatically made. versus being a hand insert. You can do hand inserts in lower volumes like prototype tools, but basically what it is, it's a slide or a lifter that is in that area of the tool that moves in that direction or that line of draw as the tool opens. You can have those mechanically powered with hydraulics. You can have rotating cores with a rack and pinion. You can have rotating cores with an actual motor if you need to. Depending on what your volumes are and how complex and how much capital you have to spend into the tool, we can make it very complex. Lifters are great because they move with the ejection system, and they would release on a set angle. That can be good for internal ribs or undercuts that are underneath the part. Other things you can think about are collapsing cores. So if you have like an internal O-ring that's inside of a hole, you can do a collapsing core or threads, internal threads. You can make internal threads with collapsing cores. The problems you can come with those would be parting lines. You have to have a very well maintained tool to ensure no flash in those areas. But just as you
Yeah.
increase the complexity of your part, you're going to equally increase the complexity of the tool.
Yeah, and I think that's something you're mentioning there. So when we're talking about these undercuts, you're creating features, so something new that would have to be designed into the tool, regardless of how it's executed, right? So like some sort of plugging feature that in some way, shape, or form needs to be removed and reset every cycle. Sometimes automatic, sometimes not. So we talk about hand loaded, where an operator standing there and moving those in and out. But these are cost drivers, and I really like that you mentioned something like an internal O-ring. If I'm CNC machining a part, say I'm using either a CNC machine tool or I'm using a lathe to turn out these features, O-ring grooves are pretty common. They're like an internal tube. I'm gonna shove an O-ring down there to create a sealing surface when I put another tube shape feature through it, and that groove is an undercut, but there's tools available for this. You mentioned something like that is a scary word for me in molding collapsible core, but I see these sometimes as traps or something that uh, you know, may add a lot of cost. It may change the design approach or considerations from the customer due to the cost drivers. What type of other traps do you see, or like things that a customer may not see as a big deal, but they actually can drive cost or lead time, or possibly have like mismanaged expectations?
Yeah, so a lot of times the trap is kind of those undercuts or those simple features on the design, right? You're just like, oh, I'm just going to add this little bit here. A lot of times that little bit can trickle down into a rather large snowball. You want to make sure that keep it simple. If your design can afford a simple feature in that area, a simple solution can be provided, and that's usually a low cost.
Now, do you ever see needs for splitting parts? I know sometimes if I'm CNC machining or I have a design for CNC machining and it has, say, like a pocket that would have to have a really long tool reach to hit. Sometimes it's cheaper, particularly on like low to mid volumes, to split it into two pieces, so they're each machine designs that could be approached with shallow tools and then combined together with some bolts and pins to line up. Do you ever see that need when I'm designing for molds, like where it may make sense to have two molds for lower cost versus like a more complex upfront mold with a single
Yeah,
body
so
tool?
those are cost drivers, right? So, if you are creating some undercuts or some features that are very complex, maybe it's even as simple as just you can't make a uniform wall thickness, but you really need it. You can split that part into two. There's different ways you can join those parts. One, you could glue them. Two, you could sonic weld them together. You could do mechanical fastening with screws and bolts, as you mentioned. Depending on the material selections, those are options. But then another choice would be, hey, we can just overmold it. So you could take that same part design and get a different material that you can overmold over the top of your substrate to help split and make the end feature that you need.
So yeah, overmolding is kind of that secondary process where you create the substrate, you create the under part, and then you mold a new material on top of that. So the final thing is still a part. It's a thing, but it just has gone through essentially at least 2 molding cycles for it. Um, and I was actually chatting with a customer the other day about a design where they were trying to make it overly complex and splitting it up. And I was like, oh gosh, I know I've seen this real world example around. And I went upstairs to my fridge, which, by the way, I recommend doing if you're ever designers, just look around you because there's a lot of cool ideas out there. But I was looking at the design for a Parmesan cheese lid, where it's essentially 2 pieces. That the flex hinge itself is actually a separate piece from the cap that goes around the body, and they're plugged in together. I'm not sure if they're ultrasonically welded or not, but it was just one of those things where you could make something that is very clever and very tough to tool up, or you could just do 2 essentially flat pieces and bond them together and make something very scalable for production. The so I want to talk about, when we have these design features. You mentioned draft, so that's like the angle that helps me release a part. And I always think a good example of draft is solo cups, right? They can stack easily together, but the second I move one a little bit away from another, I have an air gap around the entire part, so nothing's dragging when I'm moving that. You talked about that uniformity, so that's designers trying to build something that evenly cools to reduce some of that like shrink or warp that may happen. Um, we're talking a little bit about parting lines, but where's a compromise? Like, where is there suggestions from the molder, and where's there something where typically the designer doesn't control it as heavily in the design process? For example, like if I look at the back of my part, I often see little circles everywhere, and so the trajectory locations. Like, how does that play in, and who has control really when I talk about those other features that have to do with how parts are ejected?
Yeah, so part ejection is very important. It's a very important process of injection molding. It's great to make one part, but you want to make sure you can get it off the tool so you can make another one. So you have to make sure that your ejector pin locations are approved from a cosmetic standpoint, but also from a functional standpoint from the molder. They can typically you would want those near any long, ribs or deep, parting line surfaces or features. You want them around features. That way you can help push those areas out. If you have sharp angles on the inside, those are great places for the part to stick on when ejecting the part. There's small little, as you mentioned earlier, Greg, those traps that people can fall into. Each part is different. They all come with their own complexities, whether intentional or not. But you want to make sure that it's that the parts can go together and come off tools, kind of like your solo cup example. You want to provide any of that or, anything that can help release the part. From the B side of the tool will help the ejection process. There's different types of ejectors you can use. You can use, round ejector pins are the most common. You can use ejector blades. You can use stripper rings. You can use sleeves around kind of a
Mhm.
core pin. If you have kind of a dome or a circular cylindrical feature, you can add what are called air poppets. Basically, that works just by, pressurizing the inside of it with a little bit of compressed air, and it kind of just pops it off of the core. There's many different avenues and techniques that can be used for part ejection.
Yeah, and this is all about evenly pushing out these parts because I think we mentioned this in our last recording about how parts need to be removed. But if you put too much pressure on just one part of the surface, that material is still warm. It's definitely like I would consider hot to the touch. It's cool enough to hold its form, but if I'm trying to release it just from one location, I may put a divot in the part or flex it in a way where it essentially will harden in its final stage with a warp. So doing that even removal is really important. And I usually see that. So if I have a chord part design, so I chord my part, which means adding ribs for structure versus thickness to try to stay with that uniform stage. A lot of times the intersection of my ribs is a good little place for a little circle to help remove those features out. But you'll see like any part has this kind of the business side, like the A side, the pretty side of it, and it has the, I'm not going to call it the ugly side, but the utility portion, which is the, I won't say ugly
Yeah.
side. I used to say ugly side. I said ugly side like 7 times now, but it's a, it's the business portion. I think any product, if you just, open up in front of you, you'll see that there's a lot of features that help it mechanically work in the injection molding process versus just the cosmetic view of it. So you're a molder. You're talking to your customers. Do customers come to you with what they think the gating approach is? So where you're injecting plastic into those parts, or is that the molder's decision?
Yeah, so I've seen it both ways. I've seen customers go through fold mold flow simulation on their parts before entertaining a molder. That's great to have that knowledge. And if you have the experience that you can support that, that's great, even better. Typically, the gating scheme can be initially recommended by the molding facility. Uh, they'll have the experience in that in mold design and mold building and mold flow and the flow of the material and specific material, right? If you choose a molder that makes one specific material very, very well, they'll have that expertise and can provide the best knowledge. But yeah, so I've seen it both ways. Either you can let the molder design that gating scheme and the customer can approve it, or the customer can go through the great lengths of doing the research and the homework to say, here's what I want. Um, and even at that point, the molder may come back and say, you know what, that's great on paper, it's great in theory, it makes for a good part, it would make for a good part, but it's just not feasible in our mold design. I've seen that as well, where you say, I want the gate right here, and it's just not feasible in a tooling application.
Yeah, and I think that, I mean, there's is very interesting. And by the way, I am a huge fan of accessibility to CAD tools. But I also understand there's a downside where sometimes it makes makes the designer a little dangerous. And I have definitely been guilty of this myself too. With like, I think we could make it this way, and you listen to your manufacturer, and you understand, and sometimes that's tribal knowledge. Like, Scott, once you've been working in molding near 15 years or so, so you've probably burnt your hands a few times where on the stove. Where this customer may have not had that same experience. I've even seen where simulation software is good, but it's not perfect. Like, it should fill, but it definitely won't fill. And here's why, and like a glass fill variant or something like that, and we work with some different approaches to help make sure like the part is full, fills up completely. You don't have um, any features that are incomplete. I so I oh,
Yeah, so the
go ahead, Scott.
simulation's a great thing, but it's still, there's a lot of features and a lot of aspects of it that it can't dictate, right? So it's going to be assuming a perfect cooling pattern or around a cooling line with a set temperature. Well, in reality, you may not have that perfect flow of coolant. You may not have that perfect flow of gas escaping the tool. Or you may have better, right? You may have more venting in areas than the simulation has. So you have to keep in mind it is a simulation. It is taking a look at perfect situations or perfect parameters that are set in that simulation. So just proceed with caution. It's great information. I highly recommend it, especially from a shrink analysis of the part to help tooling.
Oh yeah.
And it can tell you where to vent, where the linda fill to be. Pretty, it's pretty accurate on cycle times and pressures, but you just have to proceed with caution when when it may be throwing up a red flag that may not be, exactly aligning with the tribal knowledge of a facility.
They're guidelines. The simulation is
Absolutely.
guidelines. It's better every day, and I think there's certain software we use on a more professional level that is much more accurate. But it's a mix. It's a mix of kind of experience, tribal knowledge, even budget. What are we looking to achieve? What are your estimated annual volumes? That may affect the tooling approach a heck of a lot, actually, depending on your quantities and budgets and what type
Yeah.
of trade-offs are required there. So I have a one more design question, and then I want to talk more about finish this off talking about like what a molding project timeline looks like. Uh, but can a design change once the molding process is started?
Yeah, it absolutely can change. Depending on the complexity of the change, it will have equal complexity change in the tool. If you know of an area that you may want to change in the future, it's great to have that information up front because you can design the tool in a way that will accept an insert, after the tool's been made in that area, or you can go ahead and make the insert now, and that can help cut costs on making those changes. If you make the tool in a complete solid and you come back and say, I want to put a pocket right here. Well, if there's a water line or something below the surface of that tool that wasn't thought out ahead of time, you could be making an entire block. But if you knew that ahead of time, you can core out just a little bitty area and route the water around it and make it very lower cost for those changes.
And that water you're talking about is those cooling channels that are kind of beneath the surface of the tool itself. So right by your core and cavity features, there's actually channels within the tool that are running water through to help it cool between like during the between cycles there. And I will say, like, when we talk about that mode design, we want to kick off appropriately because you don't want too many, major changes, like an entire feature just
Yeah.
appears all of a sudden after we've cut metal. To your point, Scott, and also sometimes when there's tolerances or light grooming, I think something I've heard you say before is steel safe. So like when would I like first off, what does steel safe mean on a feature, and like when we usually approach like something in what I consider like a steel safe
Yeah,
condition?
so a lot of times you'll see this on round features or round parts that need to mate together. You'd want to make sure that you have the steel or the stock of the tool available to make the hole larger or smaller. And for instance, if it's um, like a insert hole or like a core out for a plastite screw to go into, you would want to take a look at that and say, okay, if I need to add plastic, that's removing steel, and if I'm going to remove plastic, I have to add steel. That's probably the best way to look at it, on it from a steel safe standpoint. So if I'm adding plastic, removing steel, that's going to be a steel safe activity. Steel safe activities are a lot lower cost and typically have a shorter lead time.
Yeah, because you're machining away material that exists versus trying to build up or
Correct.
create something new in that feature. And yeah, I think it's something. Sometimes we see that with grooming for tolerances or fit that again, CAD may say it fits, but then in practical use, you may find that there's some interference there, especially when you're working with off the shelf components combined with
Yep.
your custom molded part. And speaking of that, we mentioned before like this idea of T1s and kickoff in a previous show, but I'd love for you to just kind of walk through like what is a typical injection molding timeline when we're working with customers from that development phase up through their production samples and getting their first set of stuff.
Yeah,
What does
one of the
that
great
look like
benefits of
typically?
Xometry is the quick turn and the quick lead times. So if you're going through a prototype stage and you're wanting to use injection molding as your prototype, with Xometry, you'll request a quote. You'll get the quote from the time of purchase. You'll get what's called a DFM. It's a document for manufacturing. It will guide the build and design of the tool. You'll get that within 48 hours. We're looking for approval from that within 72 hours, and once we have the DFM approval, we will begin the tool build. Depending on complexity of the tools, that could be anywhere from a week and a half to about 4 weeks. That you would get what are called T1s, first trial parts. Basically, you put the tool in, You inject plastic in, you may not make a full part. It may not be cosmetically correct, it may not be dimensionally correct, but at least you learn how that process is going to go. Those are not the parts you would get. Those are called T0 parts, the initial trial, and then T1 would be the trial of parts after that initial trial. Sometimes you require that, right? Depending on complexity of the part. Sometimes, your first attempt is a fail, but and that's the T0. Then the second attempt would be a T1. Typically, we're looking for those to be about 85% conforming to the part print. With Xometry, we put a plus or minus 10 thousandths tolerance on a lot of our injection molding projects. If you're looking for tighter tolerances, we take that into account up front in the DFM stage, in order to make those areas easily groomable and meet your custom, your expectations. But typically, it's about 4 weeks after a purchase order that you'll be receiving parts. Those parts should be form fit function for you. And then once you approve those parts, we have a standard 15 days to get production parts produced. From the day that you tell us that T1 part is a good part. So with that, you're looking, what is that, about 7 weeks for a production order of parts from purchase order.
And that makes sense. So that's a typical, like a typical production run, and that's full kit and caboodle. So you're getting pieces in the middle, and I think that's something really interesting to talk about too. Is injection molding? It's a little bit different because it is plastic, right? It is, there are things that happen when the part is molded into the cavity and cooled down, and you're building these cavities based off. Are based on the CAD design, offsets for the material chosen, for example, like scaling up. And then these T1s are an opportunity as a designer or the product developer or the stakeholders to go and take a look, make sure that they can raise their hand and say, this needs to be modified, or this is great, sail forward. And it's really important because it doesn't count as a production unit, right? So you're getting like 10 samples or something like that, and they're very useful in that phase, because we don't want to make 1,000+ products that don't fit your needs, like don't fit the customer's needs. So it's about ensuring success of the project, about doing those changes before they're 10,000 pieces made. And once we do that, and we're verified to go through, that tool is set. It's consistent. It's repeatable, and it has all those benefits that we look at for molding. Like you're starting to amortize cost of the tool and the parts. Things start to get very, very cheap over quantity, and you have very clean, consistent products. Scott, I think that's an awesome place for us to end this conversation. And again, there's so many more things I want to talk to you about that I'm writing little notes for future events. But I really, really appreciate the time with you. And yeah, got any last words or tidbits that
No,
I
all
should have been
good.
asking you
I'm
about?
doing great here.
All right, thanks so much, Scott. All right, well, have an awesome day, and really appreciate you joining us for Manufacturing Explained. Manufacturing Explained is a Xometry production. Xometry offers instant quoting and over a dozen processes, from 3D printing to sheet cutting to machining to molding. Xometry is your one-stop shop for manufacturing.